Hello everyone, my name is JT, and I like to cook and talk about science, so if you enjoy either of those things, then this is the channel for you. Today, I'm making some sourdough bread and talking about if I had $1 for every time I told someone that I was studying physics and they reacted in shock or said, "Ooh, I always hated physics," then I wouldn't need to study physics anymore. So that begs the question, what even is the point of doing physics? To understand that, we first need to make it clear what physics actually is. In its purest form, physics is the attempt of humans to establish a set of laws that allow us to predict the behavior of nature. What are these laws? A law is simply a mathematical statement that makes a claim. Newton's first law, for example, simply says that the velocity of an object will not change unless it is acted upon by an outside force. Notice that this statement makes no effort to explain why this is the case. It simply states the claim, and you are expected to believe it. This distinction is what sets a law apart from a theory. It is a common misconception that a theory is intellectually weaker than a law, and that a theory will eventually become a law if supported enough. However, this is not the case. The difference between a theory and a law is that, like I said, a law simply makes a claim, while a theory explains why something happens. For example, the theory of general relativity explains why gravity works, in addition to providing a mathematical set of equations to predict the effect of gravity on nature. So I guess I should amend my first statement to say that physics is the attempt by humans to formulate a set of laws and theories to predict and explain the behavior of nature. So we know what the difference between a theory and a law is. Now, how do we establish these laws and theories? Well, there is more than one answer to that. Going back to our example of Newton, he used experimental data that had been collected previously by Kepler. As he read through these logs of numbers that recorded the orbits of various stellar bodies, he was able to determine a formula for the law of universal gravitation that successfully explained why the planets moved the way that they did. In other words, Newton used data and essentially guessed until he found the right formula. Purists might say that this is the wrong way to go about things, but this is a method that has been used successfully in a number of different fields to create very effective models. In addition to this method, one could also start from what are called first principles, or the most basic terms of breaking down a problem. By breaking down a problem into the simplest terms, it is often possible to find a simple way to mathematically represent the system, which can then be built upon and expanded to account for more complexity. Theories are often developed in this way, as it helps to establish an explanation for why something works, and not just what it does. All of what we have mentioned so far is just half of the picture. You either use data to guess a model, or you derive a model from first principles. But what do both of these methods require to establish them as a law or a theory? Experiments. It is conventional to break down the work of physicists into two categories: theoretical and experimental. Theorists spend their career mastering the various mathematical tools used to build models and develop theories, while experimentalists use technology to find innovative ways to confirm or contradict the predictions of the theories developed by the theorists. However, it can also happen in reverse. Thinking back to our example of Newton once again, he used the experimental evidence collected by Kepler. Additionally, the development of quantum mechanics in the 20th century was driven primarily by a series of experiments that forced physicists to rethink everything that they thought they knew. So sometimes, the experimentalists do something that makes the theorists have to change or recreate their models. And while I am biased as an experimentalist, it can be argued that neither side of physics could exist without the other. A few unique physicists, the most notable of which was Enrico Fermi, have managed to toe the line between theorist and experimentalist and produced groundbreaking work in both fields. However, most just dedicate their career to specializing in one or the other. To summarize, no matter what the specialization of a physicist is, the ultimate goal is to figure out a way to explain the behavior of nature and predict what will happen next in a system. And this mission worked pretty well in the early days of physics. At that time, roughly throughout the 19th century, most physicists would have considered themselves to be determinists, meaning that with enough physical knowledge of a system, it should be possible to perfectly predict the behavior of that system. In other words, if the system is the universe, and we knew the current state and initial states of all the particles in the universe, then we should be able to perfectly predict the future using only physics. However, this idea was turned completely upside down with the invention of quantum mechanics, and primarily by the discovery of the uncertainty principle. The uncertainty principle states that we cannot know everything about the state of a particle with perfect precision. In order to measure some properties, we inherently disturb the others, and therefore change the state of the system. This leads to the foundational idea of quantum mechanics, that the behavior of nature is fundamentally probabilistic and not deterministic. In other words, we can only know the rough probability that something is going to happen, but we can never be 100% sure. This intellectual upheaval left many great minds of the 20th century feeling unsatisfied and longing for the good old days of determinism, including Albert Einstein, who spent the remainder of his career working to prove that the lack of determinism in quantum mechanics was simply a mistake in reasoning by its formulators, and not an inherent quality of nature. He was, however, unsuccessful in this endeavor, and to this day it seems that quantum mechanics provides one of the best models for understanding nature that has ever been created: the Standard Model of particle physics. The Standard Model is the culmination of work from the mid to late 20th century, and it describes all of our current knowledge of nuclear and particle physics. Despite strong efforts by experimentalists to create a way to disprove or expand the Standard Model, it continues to stand strong. But wait, we still haven't answered the question that we set out from the start. Why do we do physics? What is the point of creating all of these models and spending so much money on massive experiments just to say that we found one more particle that we can't even see? Well, as I record this video and cook this meal and speak into this microphone and edit this collage of clips that is transmitted across the world to your computer, we enjoy the fruits of the labor of physicists and engineers throughout history, who have spent their lives trying to understand how things work. The CPU in your computer or phone that you're watching this on is the product of quantum mechanics, as are the improvements in streaming and media digitization. But, in addition to all the practical uses, we have to acknowledge the fact that we do it because we like it. Yes, as hard as that may be to believe, physics can actually be fun. Being able to speak with nature using this special code language is a privilege, and if you're still watching this video, I expect that you probably feel the same way. So yes, physics can be productive, but it is also a way for humans to express themselves and further connect themselves to the universe around them, much in the same way as art. If you ever wonder why humans don't build giant, beautiful structures like they used to, just go look up images of particle accelerators. And as always, don't forget to season your food with your heart and to season your mind with science.